Okay, welcome to an example using binary variables. So this is a toy manufacturing example. I encourage you, pause the video right away, read through the description of the problem, see how much you can get, okay? Once you've given it a try, unpause the video and resume, and we'll kind of talk through all the steps of setting up this optimization problem using binary variables. Okay. So we've got a toy manufacturer wanting to produce toys. We see that we've got setup cost and then also a profit. I guess this should actually be profit per toy in as dollars per toy. Let's maybe actually give some names to the parameters in this problem. So this, I'll sort of call this setup of toy T. And this we'll call profit of toy T. We'll use kind of T as our index for our toys, T being 1 or 2, depending on which toy we're talking about. So that's that information. Down here, we've got production rates in units per hour for each of the toys. And so I'll go ahead and call these values in here as rate of T comma F for the rate of toy T at factory F. Or maybe I should write them as FT. Doesn't really matter as long as you kind of are consistent in how you would then plug them into the formula. And then here are sort of our limits on production time. And so I'll maybe call those, and those are for factories 1 and 2 respectively. And so I'll call those time of F. Okay. And the goal is the manufacturer wants to know how many new toys to produce at which factory. So this is a scenario where we want to know not only should we produce a toy at a factory, but also how many. So it's a combination of how much and as well as the yes or no question of should toy T be produced at factory F. Okay. And so that will influence our choice of decision variables. We'll have pairs of decision variables that will be working together. So we'll have a decision variable X TF, which is answering the how many. It's going to be the continuous variable. Maybe it should actually be an integer variable, but we'll let it to be continuous. Kind of a rule of thumb is try your variables as continuous, even if you think they should be integer, and see if it will solve. Continuous variables are much more efficient in the problem, and only switch it to integer variables if you have to. So, so there's our XTF, and it's how many toys of type T should factory F produce. Okay, and then we're going to define a corresponding binary variable Y of TF, which is going to be should any be produced. Okay, and so I'm going to say, I'm just going to actually write what we want this YTF to be. Note, and I've had some students kind of make this mistake in the past, like writing down what you want a variable to do isn't the same as putting in the constraints to actually make it do what you want it to do. Okay, and so we're going to have to add the constraints that are going to give it this behavior. So we want YTF to be 1 if XTF is positive, bigger than 0, and we want it to be 0 if XTF equals 0. Okay, and so the Y variable essentially turns on and off as X turns on and off, but it's the binary version of that continuous variable. Okay, so those are our two decision variables. Note that we'll have 4 of each because there's 2 toys and 2 factories. Okay, if you had more toys and more factories, you could just scale this up and kind of have T go through all the toys and F go through all the factories. Okay. So that's our decision variable. Now let's get into our objective next. And our objective, we're going to want to look up here. So we've got profits tied to each toy type, as well as setup costs tied to each toy type. Okay, and so we're going to want to think of the profit from those toys and the setup costs. And so profit is we want to our objective is we want to maximize sort of our net profit, taking into account those costs. And so that's going to be equal to really for each toy we make, we get the profit. And so that's going to be X TF times profit. And the profit doesn't depend on the factory, it just depends on the toy. And then we're going to have to subtract off how much, essentially our setup costs. So if we set up a toy, then we need to pay that setup cost. And so we'll take YTF times the setup for that toy. Okay. And so if we just consider a single toy at a single factory, this would be the net profit for that toy at that factory. Okay, notice it doesn't depend at all on the factory. Now we need to know that for each of the toys at each of the factories and sort of adding all those up, some of which are going to have zeros for the variables, and those are going to essentially not affect the sum. But in our objective, we don't know that yet. And so we have to let the optimization decide which of these actually are non-zero, but just write out the expression. Sort of at the beginning, you want to pretend everything is non-zero, and so let the optimization decide. So we're going to sum over all the toys over all the factories. Okay, so when we implement this in code, this will be a sum over with the index of both T going from 1 to 2 and F going from 1 to 2. And we're going to take the number of toys times the profit per toy, and whether or not we produce that toy at that factory times the setup cost. Note, this is either 1 or 0. If this is 0, this term disappears. If it's 1, we subtract off that cost. Okay. So that's our objective. Now we can go ahead and get into our constraints. There's going to be several constraints in this problem. We'll deal with them one at a time. And I always encourage students, as you're sort of thinking through this, maybe go back to the problem and underline each sentence that you think is going to be a constraint, right? And then write that constraint out in words, which is usually just taking the text from the sentence, but you're not always going to be given problems straight up. And so think about what each constraint is in English before thinking about what it is maybe in mathematical notation or coding notation. Because if you can't explain it in English, you're unlikely to be able to implement it in code or in math. Okay. So first constraint will sort of enforce the relationship between the X and the Y variables for the corresponding X and Y variables. Okay. In that we want X to essentially turn on Y, or conversely, you can think of Y as turning off X, meaning that we want Y to be forced to be 1 if X is greater than or equal to 0 or greater than 0. And we want X to be forced to be 0 if Y is 0. So the way we do that typically is we'd have something where we'd have X is less than some big M times Y. In practice, you always want to sort of figure out what that big M should be in the context of your problem. And you can always substitute in anything that would be a reasonable upper bound on the value of X. So it's maybe worthwhile thinking for a second, what's the maximum amount of toys we can produce? And maybe it's a little bit kind of thinking back to maybe distance rate time equations, except for now this is toys rate time equation. In that kind of looking at production rate, number of toys produced divided by time equals rate. Okay, and so number of toys is then going to be rate times time. You can kind of rearrange this in a couple different ways to get what you want. So, but kind of number of toys per time is your rate. Okay, and in this case, we want number of toys. And so maybe rearranging this number of toys equals rate times time. Okay, and so the most toys you could make of any type at either factory is the rate for that toy at that factory times the amount of time available for that toy at that factory. Okay, and actually we have both those quantities here, and we've given them names, rate TF and time of F, and so those are going to be essentially the upper bounds on XTF. Okay. So we're going to kind of factor that in here and have that. So let me write this out in words. Cannot produce without the setup cost. Okay, that's essentially the relationship here, is that the Y variables are going to turn on this negative cost over here. Okay. And so that's going to be implemented as X TF is contingent on Y. And so we'd say that's less than or equal to some constant times Y. That constant is going to come from our parameters of rate TF times time at factory F. Okay, that's playing the role of our big M. Okay, and that's going to be multiplying by Y TF for T equals 1 to 2 and F equals 1 to 2. Okay, so there's going to be actually 4 copies of that constraint, one for each of our X, Y variable pairs. Okay, so that's cannot produce without putting in the setup. Okay, now let's actually return to this table and think about, well, we have limited time here, and we're not actually assuming that we'll kind of hit these maximums here by only producing the one toy in the factory. There is the potential that we might make more than one toy in a factory. And so we got to put production limits in here, in that if we try to produce 2 toys in the factory, they've got to share this time. Okay, and so in that case, we might need to rearrange this formula one more version of that, and that is that time is equal to let's divide rate over the other side, toys divided by rate. Maybe I'll write that one on this side, and that time taken equals number of toys divided by the rate. Okay, and so we can think about the time used to produce toy 1 at factory 1 would be the number of toys of toy 1 at factory 1, which would be X11 in this case, divided by the rate 11. Okay, and so let's actually turn that into a constraint up here. So I'll call this production time limits. Okay, and so if I think of how much time is taken by each individual toy, that's going to be the number of toys, which is XTF is what we're deciding on, divided by rate TF. Okay, and I can do this, I can divide by rate TF because rate TF is a parameter, not a variable. Okay, it's a given number that we know from our problem. Okay, and so this is the amount of time taken by toy one at factory one, or if I kind of, for each toy at each factory. And then I need to add that up. So I'm going to add up that for both the toys. Okay, so I'm going to add for toy one plus the amount for toy two at a given factory F. Okay, and that has to be less than or equal to the time that's available at that factory F. And I'll get one of these constraints for each F equals 1 to 2. Okay, so I'm going to get 2 copies of this constraint. I'm going to have this constraint for factory 1, where I replace the F's with 1s. And I'm also going to get this constraint at factory 2, where I replace the F's with 2. So that's the production time limits. Let's think about what else factors in as a constraint. And really, that's it. Okay. Kind of looking back here at the given information. I've got sort of the production rates, and I've got the costs, and then I've got this idea of setup costs, which forced me to have the pairs of decision variables, one continuous and one binary. Okay, so that is the kind of setup and constraints for this toy setup. Okay, let's go ahead and implement this in R. So this is another point where I encourage you, pause the video, give this your best try on translating this into code. I wrote it in a way that looks very similar to how we'll code it up. The main thing to kind of remember is that kind of your mathematical sums get replaced with sum over when we're using the OMPR package. Okay, here we are in R and kind of the implementation. I've gone ahead and sort of created my parameters up here, a matrix for the rates, a couple vectors for setup, profit, and time. And then I've set it up with X variables as being continuous and Y variables as being binary. Kind of T going from 1 to 2 and F going 1 to 2 for both of them. My continuous variables have a lower bound of 0. Here is that objective. I'm going to sum over the profit times XTF minus the setup cost times YTF. And I'm going to sum that over both toys and both factories, and I want to maximize that. This constraint is my sort of turning on and off the X and Y variables together. And so the XTF is less than or equal to, this plays the role of my big M, which is sort of the maximum that I could produce at any factory, times YTF. T equals 1 to 2, F equals 1 to 2 as well. So there'll be 4 copies of this constraint. And then this last one, I'm going to sum over the ratio of XTF divided by rate TF. I don't think I actually needed this one. I think I was debugging something earlier and stuck it in there. I'll try removing it and seeing if it makes a difference. And then that has to be less than or equal to the time that's available at that factory. Okay, let's go ahead and run this. And here's our solution. We'll get a net profit of, let's see, $572,400. This is how many, looks like we're going to be making toy 1, because the first index is T, the second index is F. We're going to be making toy 1 at both factories, and we're not going to be making any toy 2. So apparently, toy 2, even though it had a higher marginal profit per toy, also had a larger setup cost, and the setup cost just didn't pay off in this case to make it worthwhile with the availability of time that we have at the different factories. And so because we have a positive amount for x11 and x12, we see that y11 and y12 are both 1. Okay, the y variables are binary, and so they're always either 1 or 0. Note you don't have to put any lower bounds or upper bounds on the binary variables. That's sort of taken care of automatically by saying I want these to be binary. They're going to be 0 or 1 only. Okay. That wraps up this example. See you in the next video.